Hello, dear students. I have been asked to do number 13 from the problems I asked you to work for Wednesday, which we didn't get a chance to go over in class. This is going to be an amazing video, and you're really going to finally understand implicit differentiation with respect to time for related rates. So here goes. Oil spilled from a ruptured tanker spreads in a circle whose area increases at a constant rate of 6 square miles per hour. How fast is the radius of the spill increasing when the area is 9 square miles? So first what I'm going to do is to give you the calculus that you would have to do, and then I want to give you a more conceptual explanation. So here is our oil tanker, and we have dA dt is 6 square miles per hour. So first I'm going to just give you the calculus here. So if we want to use the implicit differentiation with respect to time, we know that the rate of change of the area is dA dt. That's 6 square miles per hour. And we want to know the rate of change with respect to time, that's what they mean by rate of change, of the speed at which the radius is changing when the area is 9 square miles. So if we just do the regular implicit differentiation, we're going to start out by looking at the equation we have. A is equal to pi r squared. We know that. The area is pi r squared. But we want dr dt. That means we have to solve for r as a function of a. Excuse me. So we have dr dt is equal to, this is a over pi to the 1/2. So that's going to be 1/2 a over pi to the negative 1/2 times 1 over pi times dA dt. This is implicit differentiation. We're treating both r and a as if they're variables and taking them with respect to time. So when you do the calculus, you end up with 1 over 2 pi times the square root of a over square root of pi, and a we know is 9, so I put the 9 in there, times 6 square miles per hour, and when you reduce it, you get 1 over the square root of pi miles per hour. And you can download the other way to do it, which is dr dt is equal to dA dt, which is what we're given, times dr dA. Again, if it's dr dA that we need a function of r r as a function of a. So here's the other way to do it. You end up with 1 over pi. But some of you are asking me, what does this really mean? What are we really doing? So I think this is a good problem to walk through slowly and conceptually. So I'm going to move this over here. You can see my beautiful circle there. Let's move our little circle over here. So what we're really talking about is the following, okay? We want to look, what we're given is 6 square miles per hour is the area. So what that means is it's a linear function because the rate is constant. So this means as I move time, so for example, when x is about 1, right, then it's 6 times 1, or 6 square miles. Right? When it's 2, it's going to be 2 times 6, or 12 square miles per hour after 2 hours. So that's what this graph is. So the y-axis right here for this particular graph shows me the area at any given time. Notice as I move time, because time is actually the variable here. Time is the one variable that we're trying to coordinate other things with. So what you see is as the time goes on, the radius isn't going at a constant rate. It doesn't look like it's going as fast, but the area is going at a constant rate. So that's what we're really looking at. We're looking at the area increasing at a constant rate. So at 10 hours, it would have an area of 60. Okay, so hopefully so far this makes sense. So what the most important thing to remember is, remember I said that the letter on the bottom here, in this case, it's always going to be dt. The letter on the bottom is always the letter that's the actual variable. So here's our time. Now, the next thing we do is we actually want dr dt. So we want to express the area as a function of the radius, but the function of the radius is time. So notice here in implicit differentiation, that's what we're doing. We solve for r. R is the square root of a over pi. And then we take the derivative with respect to time. So what I'm going to do here, notice, is if I show you r, right, the r, we said, is the square root of, oops, that moved that too far. R is the square root of a over pi. So that's right here. This was our f of x is 6 times x. So it's f of x, which is 6 times x, divided by pi, the square root of that. This describes for every moment t, or time, you're going to know what the radius of this circle is. That's what we're really doing. That's the heart of it right there. So this tells me that at this particular moment, the radius is 2.98. As I move the time, you can see this will always tell me what the radius is. So now, if I plot this function, it looks like this. It's a square root function, which is interesting. So what it's saying is, as the area goes up at a constant function, the radius doesn't increase that fast. It only goes up at the square root, this right here. So what we're saying for r dt is this is r, this is a function of r, and this is t. So we want to show the this right here is telling us dr dt. So the slope of the tangent line at this point will give me dr dt. I want this particular one to be when the area is at 9, which is right here, 9 square miles. So this is the value of 9. I look down here, I say, oh, that's where the time turns out to be, 1.5. And notice that the slope of this tangent line is 0.56x, and that is exactly what we got when we did our calculus. So what we're really doing when we do these related rates is we're finding the slope of the r of t, which is the function that defines the radius in terms of time, even if we're given a different function, area, in terms of time. I hope this has really helped you understand a little bit more about related rates as they relate to time.